Java 25 is finally out and packed with improvements. This release brings more compact and readable code, lots of optimizations for faster execution, and overall performance enhancements. Moreover, it's a long-term support release. Here I'll walk you through the changes integrated since Java 21. So first we'll check out the features you can use every day as a developer, and then we'll dive into the low-level changes that can seriously boost performance. Let's jump in. Remember the first time you saw Hello World program in Java? It looks quite terrifying for the beginners. There is too much clutter here, too much code, too many concepts, and too many constructs for what the program does. Current changes allow writing small programs simpler and more lightweight. First, a compact form of source file is introduced that lets developer get straight to the code. Second, it is now possible to omit the infamous boilerplate of public static void main. Third, new I/O methods for beginners are added, thereby replacing the mysterious system out println with a simpler form. Behind the scenes, the behavior of the program doesn't change, but beginners could now learn concepts in the right order. Moreover, the change is useful for writing code for testing quick ideas, replacing bash sometimes. Each Java class usually have a long list of imports, and the actual code starts somewhere around line 30 if you're lucky. This also adds pressure on Java beginners as they stumble across this even before facing the scary main method. Java 25 introduces a way to import entire Java modules directly in source files, simplifying module usage, especially in small programs or scripts. For example, importing module Java base has the same effect as 24 on-demand package imports. Java team came up with the idea of import module declarations while was working on compact source files and instance main methods, which aim to reduce the ceremony to learning Java. Before Java 25, constructors were restricted by the rule that nothing could appear before a super or this call. This often led to unnecessary work and code duplication. Java 25 introduces flexible constructor bodies, allowing statements to appear before an explicit constructor invocation. These statements cannot reference the object under construction, but they can safely initialize fields and perform other computations. Now, a constructor body has two phases: the prologue, which runs before constructor invocation, and the epilogue, which runs after it. This change makes it possible to write constructors in a more natural and concise way. Next feature is unnamed variables. It introduces a placeholder for variables or pattern components that are intentionally unused. They all could be replaced with an underscore, and it lets you match a type or destructure a record without creating a real variable. The compiler no longer generates an unused local variable in bytecode. There were limitations in switch operator for some types. The following code would result in compilation error because selector expression must be char, byte, short, in, or reference type. Java 25 removes this limitation and allows more primitive types in switch operator. Similarly, the following code would lead to compilation error. This is because pattern matching is possible only for reference type. In the new version of Java, it is possible to check for primitive types. It also applies to guarded pattern matching. There is a similar change for instance of check. In Java 25, you could check if variable is a primitive type. Now let's move on to the library updates. Java 25 introduces a brand new standard API for reading, writing, and analyzing class files. Until now, developers have relied on third-party libraries like ASM or ByteBuddy to work with bytecode. These tools were powerful, but they were also unofficial and fragile, tightly coupled to JVM internals. Whenever the class format changed, for example with features like seal classes or dynamic constants, library authors had to rush to update their code. Many frameworks, for example Spring, use bytecode transformation to transparently add functionality to the code. Tools that automatically generate proxies, inject instrumentations, or weave extra logic at runtime, they all depend on understanding and modifying class files. Java 25 introduces own class file library as a stable public API. Now developers can safely read, inspect, and generate class files or even build them from scratch. The API is type-safe, forward compatible, and maintained in sync with every JDK release, so it always understands the latest class file structures. Scoped values are a new Java API that lets you safely and efficiently share immutable data across methods and threads, especially virtual threads, without using thread local. Traditionally, developers used thread local to store per thread context, but thread local has several problems. Values can leak if not removed manually, it works poorly with virtual threads, it's mutable so different parts of the code can change the same data, and it's hard to reason about lifecycle and cleanup. In modern concurrent systems, especially with structured concurrency and virtual threads, this model no longer fits. Scoped values solve these issues by introducing lexically scoped immutable bindings. You define a value that is available only inside a specific code scope, automatically cleaned up when the scope ends, immutable, and inherited by virtual threads created within that scope. Everything inside run can access the value safely, and once you leave that scope, the binding disappears automatically. A stable value is a way to achieve deferred immutability. Before Java 25, developers had two imperfect options for storing important runtime objects. First is final fields. They are immutable, safe for concurrency, and JVM can optimize them through constant folding. But they must be initialized early, usually in constructor or at field declaration. There is no way to load it later when you actually need it, for example, after reading environmental variables or connecting to a service. Moreover, early initialization can slow down startup. The second option is mutable fields. They are lazy, so they could be initialized only when needed, flexible, they can depend on runtime state, but at the same time, they're not thread safe, they need synchronization or volatile, it's easy to make mistakes, double-check lock-in bugs, race conditions. After initialization, the field is still mutable, so other code can accidentally change it, and JVM can't apply optimizations, it must assume the field may change anytime. In a nutshell, the ways in which Java language allows us to control field initialization are either too constrained or too unconstrained. A stable value is an object of type stable value that holds a single data value, its content. A stable value must be initialized sometime before its content is first retrieved, and it is immutable thereafter. A stable value is a way to achieve deferred immutability. Stable values are initialized at most once, and with them you can get both lazy initialization and immutability thereafter. It allows for JVM optimizations and faster startup. You can create either stable value or use a stable supplier. With stable supplier, you declare the initialization logic at the field definition, but actual creation is deferred. Next change is PEM encodings of cryptographic objects. It lets Java directly read and write PEM files, like certificates or keys, without external libraries. Before, you needed libraries like Bouncy Castle to handle such files. Now the JDK provides built-in API to do it easily. It defines API that converts between PEM text and objects representing keys, certificates, and certificate revocation lists. The next change removes Java's biggest pain when talking to native code. Before, libraries had to use JNI, complicated, unsafe, and platform-specific. Now, with the new foreign function and memory API, Java can call C libraries directly and manage native memory safely. Developers get faster, safer, and more portable libraries without changing a single line of code. The foreign function and memory API introduces a modern, safe, and type-checked way to call native functions directly from Java without JNI or extra C wrappers, manage memory outside the JVM safely and automatically, and do all of it in a cross-platform way. Even if you never touch JNI, libraries that you use like netty, RocksDB, TensorFlow, SQLite become faster, safer, and more portable. Libraries can call native code efficiently without changing your Java code. So basically, all major Java libraries that currently use JNI could migrate to a new API over time. Let's have a look at important changes related to garbage collection. Starting Java 25, ZGC has generational mode only. What does it mean? ZGC is a low-latency garbage collector which does the majority of its work concurrently. Non-generational GC currently stores all objects together, regardless of age, so it must collect all objects every time it runs. Generational ZGC splits the heap into two logical generations. The young generation is for recently allocated objects, while the old generation is for long-lived objects. In Java 25, only generational mode is available. Generational ZGC shows significant throughput improvement. It allows it to reclaim memory more efficiently, not needing to consider the whole heap for every garbage collection. The effect is that less CPU resources are spent doing garbage collection work. But we can clearly see the trade-off we have done. The cost is higher native memory consumption. To efficiently implement the generational support, we need to keep track of pointers from the old generation into the young generation, and it consumes memory. At the same time, it doesn't need as much heap to handle a given workload, so additional native memory usage can often be saved by using a smaller heap and still experience better overall performance. Another change in garbage collection is that Shenandoah garbage collector now also has generational mode in non-experimental state, so for this garbage collector both modes are available. Next update is related to G1 garbage collector. Change is applied for Java native interface critical regions. For G1 garbage collector, region pinning is implemented, which is essentially just locking objects in place as the garbage collection moves other objects. This allows garbage collector not to be disabled during the critical region. Let's elaborate a bit more on this. JNI, or Java Native Interface, is a bridge that allows Java code running in the JVM to call and to be called by native applications or libraries written in languages like C or C++. It's used when you need to access system-level resources or existing native code that Java can't handle directly. In JNI, critical regions are sections where Java arrays or objects are accessed directly from native code without copying. The JVM must take care not to move the associated critical object during the garbage collection. While inside a critical region, the garbage collection is paused for those objects, so it's important to keep these regions as short as possible. In previous Java versions, garbage collection was disabled during every critical JNI region. This had a significant impact on latency. If a Java thread triggers a garbage collector, then it must wait until no other threads are in critical regions. Java 25 introduces region pinning for JNI critical sections. Without disabling garbage collector, it is possible to continue to collect garbage in unpinned regions. The next Java update is compact object headers. It aims to reduce the memory overhead of Java objects by making their internal structure more space efficient. In the JVM, every object has a header that stores data like identity, hash code, login state, and garbage collection metadata. These headers used to take a fixed amount of memory, typically 64 bits, even if much of that space wasn't actually needed. With compact object headers, the JVM can use smaller or variable-sized headers depending on the situation. This change improves performance and leads to lower memory usage, better CPU cache utilization, and can improve overall performance, especially in applications that create many small objects. It can also reduce the number of garbage collections or make some operations faster. And the last point for today, starting with Java 24 and 25, the JVM introduces a series of ahead-of-time improvements, designed to make Java applications start and warm up much faster without changing application code. Traditionally, the JVM loads classes, links them, and gathers runtime profiling data only when needed. That makes startup slower and requires several seconds or even minutes of warm-up before the JIT compiler can fully optimize performance. Ahead-of-time features address exactly that problem. The first feature is ahead-of-time class loading and linking. It makes possible to preload and prelink classes before applications start, though the JVM doesn't waste time resolving them at runtime. This cuts startup delays and reduces CPU overhead during warm-up. Next is ahead-of-time method profiling. It actually saves JIT profiling data from previous runs and reuses it. So it lets the JVM immediately optimize hot methods instead of relearning them from scratch. This drastically shortens warm-up time. And the last is ahead-of-time command line ergonomics. It simplifies the use of ahead-of-time features by making them easier to enable and automatically tuned. So developers no longer need complex flags, the JVM handles most of the setup. Together, these improvements make Java applications start faster, reach peak performance sooner, and behave more consistently across runs, especially useful for microservices, short-lived workloads, and cloud environments where startup really matters. That's all for today. We've covered a lot of new features and improvements in the latest Java version, and as you can see, there is still so much happening in the language. There are also some more niche updates like in cryptography and GTK flight recorder that we can cover next time. Thanks for watching, and I hope you found this helpful, and see you in the next video. Bye!